This is just for the analysis of algorithms, right?
That's right.
Yeah, just to
I mean,
compare
that's,
them. So,
yeah,
algorithms that use recurrence.
sure, exactly. So if we use recursion in our algorithm, we can write down some sort of recurrence relation, which represents the amount of time it takes to do each step. And then we can get a bound on the order of growth. We can compare two algorithms and their running times and so forth. This is the major application of these in computer science. So, okay, so we have all these words. We're supposed to look at a linear, homogeneous, recurrence relation with constant coefficients. That simply means I have a recurrence of the form an equals c1 an minus 1. Oops, and I guess I should put a degree here, of degree k. So c1 an minus 1 plus c2 an minus 2 plus all the way down to ck an minus k. And in this case, the ci's are constants. That's where constant coefficients comes from. It's linear because everything's linear in the previous terms. There's no an squared or anything like that. And it's homogeneous. That means that there's no plus 2 out at the front or anything like that. Homogeneous just mathematically means that everything has exactly one term of degree 1, and that's it. So there's no an times an minus 2 or anything like that. And then degree k means that we go all the way down to degree k, and so we better have ck not equal to 0. So does this make sense? I should write down. So linear means that there's no ai squared, for example, so everything's linear in the ai's. Homogeneous means that there's no, everything's multiplied by exactly one ai. It's constant coefficients. This means that the ci's are real numbers. They're just constants. And what else? Degree k. This means that ck is not 0. Does this make sense? Are there any questions so far? Rob?
But the C1, C2, CK, they can be different from each other.
Yes. Yes. Exactly. So we could have something, the ci's don't have to equal each other. We could have, well, for example, I can put a 3 here. And then this first example is a linear homogeneous recurrence equation with constant coefficients of degree 2, because I go down 2 steps.
You have to be stepping down each, the n by 1 each.
Yeah, you step down each one by n, although we don't necessarily, some of these constants may be 0. Okay. So for example, this guy is a linear homogeneous recurrence relation with constant coefficients of degree 3, because the final guy is this 3. Oops, yeah, you're right, sorry. So does this vocabulary make sense? Degree 3 is this last. It's the pardon?
The first one is degree 5 because
it's degree. So this is degree 3 because we've gone down 3 steps from an minus 1. This or from an. This depends on something that's 3 removed from our starting point. So, in theory, this depends on an minus 1, an minus 2, and an minus 3. even though, I mean, these sort of don't appear, but we have to go all the way down. I guess maybe the point is that when we're solving these, if we have something like an equals an minus 3, and we have an initial, like we want to get a unique solution, we sort of have to have base cases, and in this case we'd have to have 3 base cases in order to be able to continue our recurrence. So we'd have to start out knowing what A0, A1, and A2 are. Once we know that, A3 is just going to be 5 times A0, A4 is going to be 5 times A1, and from that point on we'll know exactly what the rest of the sequence is.
I thought that was 5 A sub n minus 3.
Oh, sorry.
Would any 3 base cases be enough? Or
Yeah.
Have to be A0, 1, 2?
No, they could be any 3 base cases. They have to be consecutive, and you could start anywhere along. But I guess today mostly I'm going to be starting at A0 because mathematicians like to start at 0 as opposed to everyone in the rest of the world who likes to start at 1. The question then is, when can we write down a formula that simply tells us the nth number, not using this recursion? So what's a closed formula for an? And the answer is, well, we have some equation like this, and our best guess is going to be, well, suppose an is just some number to the nth power. Often our order of growth is, 2 to the n or something like that, so this is sort of a first guess. Question is, what's r? So if we now plug in an equals r to the n into our recurrence relation, so then r to the n is equal to c1 r to the n minus 1, because here I have an an minus 1, so I have r to the n minus 1, plus c2 r to the n minus 2, all the way down to ck r to the n minus k. So I get this equation in r, and now I want to solve for r. So to solve for r, well, first I'm going to divide through by r to the n minus k. So I get this guy down to just a constant, and then all these exponents go down by 1. So this becomes r to the, let's see, n minus k is r to the k. Then n minus 1 minus n minus k is k minus 1. I get k minus 2, all the way down to ck times r to the 0. So I get this equation in the r's, or in r. I bring r I bring all this over to the other side, and I get r to the k minus c1 r to the k minus 1 plus, minus ck equals 0. And so what I end up with is that r must be a root of this polynomial, which comes from here. So I just said, okay, let's suppose this guy is a solution. This is going to be my first guess. Then I plug an equals r to the n, or, a to the n minus 1. A sub n minus 1 equals r to the n minus 1. This is going to be true for, I'm assuming this is true for all n. Then I plug this into this equation, and I get this equation here.
Is there any reason why one would think that A sub n is of the form r to the n?
Well, it seems like a reasonable guess because we've sort of seen
A lot.
things popping up like this. We've often seen things that look like a constant times 3 times 2 to the n or something like that. That often seems to pop out when we've done some of these examples by substitution. Maybe let's do an example and we'll see why. Oh, but first I should tell you, this guy is called the characteristic equation. Associated to our recurrence relation, and the roots are the characteristic roots. It doesn't seem obvious at all yet that if we do find a root to this equation, then it's actually going to be a solution. But it is. Should we prove that? Maybe. Let's do an example first.
Okay.
So suppose we just have this recurrence relation. And suppose we have the initial condition A0 equals 2. Then, well, we can just solve this by substitution. We just sort of repeat, and we get, well, this is equal to 2 times 2an minus 2 equals, so this is 2 squared an minus 2 equals 2 squared times 2an minus 3 equals, well, let's see, this is 2 cubed an minus 3. Finally, if we continue, we're going to get something that looks like 2 to the k an minus k. Now to get down to 0, I have to let k equal n. So what I get is 2 to the n a sub 0. A sub 0 is just 2, and so this is just 2 to the n plus 1. So this maybe wasn't a terribly enlightening example, but I mean, it does give us something that ends up being some exponential thing, and so maybe it gives us some reason to hope that, yeah, really, we will have an exponential appearing in our solution. So here's the theorem. The theorem says that this does really work. Like, we really can take the roots of this characteristic equation and find the right answer. Okay, so what does that mean? Well, so if I have my characteristic equation here, and this has roots R1 up to RK, and these guys are distinct. Then I'm going to have a solution this isn't supposed to be sum, it's supposed to be this. So the sequence an is a solution to this recurrence relation. If and only if n is equal to alpha 1 r1 to the n plus alpha 2 r2 to the n plus alpha k r k to the n, where alpha i's are constants. Okay, so here's our recurrence relation. And I claim that if I write down this polynomial, so my polynomial is going to be r to the n equals r to the n minus 1 plus 2 r to the n minus 2. Oops. Two r to the n minus 2. And so now if I subtract these guys over to the other side and divide by r to the n minus 2, this turns into r squared minus r minus 2 equals 0. And let's see, so this guy has roots r minus 2, r plus 1 equals 0. So when we do these problems, we now have to remember how to factor polynomials. Hopefully the ones in the homework don't factor terribly badly. Let's see, so this guy's okay. So now what I claim is, oh, I guess we better have initial conditions too. Anyone's favorite initial conditions?
A0 equals 17.
Okay. So now my solution is going to be different from what I wrote in your notes, but that's too bad. Okay, so claim my solution is going to be of the form an equals alpha 1 times 2 to the n plus alpha 2 times minus 1 to the n. Now I have to find out what alpha 1 and alpha 2 are. So to do that, well, fortunately I have these two starting conditions, so I can say let's see, so if I look at A0, if I look at my formula, well, A0 is supposed to be alpha 1 times 2 to the 0, that's just alpha 1, plus alpha 2 times minus 1 to the 0, so that's just alpha 2, and this is supposed to be 17. And then A1 is supposed to be 23, and that's also 2 alpha 1 minus alpha 2. And now we see the use of all this linear algebra we learned. We have to solve these two equations and two unknowns. More generally, I guess we'd have k equations and k unknowns because we would have had to start with k initial values. So let's see, if we add these two equations, we get 3 alpha 1 equals 40. Yeah, so alpha 1 is equal to 40 thirds, and if I subtract twice this from this, I get,
You have your alpha 1.
oh yeah, sure. So I just have to subtract this from here, and so alpha 2 is 17 minus 40 thirds. Let's see, 30, this is 51 thirds. So I get 11 thirds. So my final answer is an equals alpha 1, so 40 thirds times 2 to the n plus 11 thirds times minus 1 to the n. Does this work? I mean, that seems like this really convoluted formula, first of all. Second of all, we have all these thirds. I mean, are they really going to cancel each other out? They're supposed to cancel each other out because I should get integers. I mean, this recurrence equation is nice enough, and I started with integers, and I'm always just multiplying by 2 and adding things. So let's work out a couple terms. So let's see, it goes 17, 23, and then it's the one previous plus twice the one previous to that. So I can't add very quickly today. 57. Okay, and then let's see, 46 plus that. And then 114, so that's 217, 206, 423. Well, sure, I don't want to go any further, so let's check this one. So this is A0, A1, A2, A3, A4, A5. Okay, so A5 is supposed to be 423. And over here I claim that it's 40 thirds times 2 to the 5th. So 40 over 3 times 64. And then minus 11 thirds.
2 to the 5th, 32.
2 to the 5th? Oh, good. Because that was going to be a really big number.
And wrong.
Yeah. Okay, so
So it's 1280 over 3 minus 1170. 1269 over 3. Lo and behold, it's 457.
yeah, so 1269, and I can do this. So 420.
But
So-
you knew you were right at A4 because it ended in 17.
Anthony,
When you went from R sub n, or R to R.
from here to here.
Yeah. What assumption were you making?
Oh, I didn't make, I guess I assumed that R was not 0. So what I did, first I should write this out better than I did. So I had R to the n equals R to the n minus 1 plus 2 R to the n minus 2. So now I just bring these over to this side, and I get R to the n minus R to the n minus 1 minus 2 R to the n minus 2 equals 0. And now I divide by R to the n minus 2. And so this cancels out all but 2 of the r's here, all but 1 of the r's here, and all of the r's here. So I'm left with r squared minus r minus 2. I'm not exactly sure what's going to happen right now, but let's try and solve this recurrence equation by substitution, which is the only method we know of so far. Maybe this is going to be a mistake. Well, you know, we make mistakes in math sometimes. So I'm going to start out with maybe some nicer, well, I guess it doesn't matter. Okay, so suppose I start with this, and I want to try attacking it with substitution. And end up with, well, let's just substitute in for an minus 1 right now. So this becomes an minus 2 plus 2an minus 3. And I have to carry along my 2an minus 2. So I get 3an minus 2 plus 2an minus 3. Now if I go to substitute in for an minus 2, I'm going to get 3 times an minus 3 plus 2an minus 4. So this ends up being 5 an minus 3 plus 6 an minus 4. This is kind of nice. Okay, so let's do it again. 5 times an minus 4 plus 2an minus 5 plus 6 an minus 4. Well, what I get is, let's see. (11an minus 4). That doesn't seem quite right. It's not, because I added wrong. 10an minus 4 plus 10an minus 5.
By 5a minus 1, not 6. 3, 1, 2.
Had I done that right? Isn't it 3an minus 3 plus, oops, oh, this is 6. Okay, so I was hoping we'd see a pattern at this point, and I don't. At this point, of course, I saw a pattern, but then it went away, so that's too bad.
This just emphasizes why this method's
Well, yeah, I mean, certainly this shows us why this is a better method than just sort of substitution and trying to figure it out. I was hoping we would be able to see why we would guess some power of R or some combination of powers of R using this. I guess it's not obvious from here. It might be obvious once we start doing this linear algebra method. So if you suspend your disbelief until the end of class, then maybe we'll get some nicer answers.
Let me suggest some patterns. I don't see how to put them together yet. But if you put the 3an minus 2 plus 2an minus 3 on the board,
Mm-hmm.
followed by 5an minus 3 plus 6an minus 4, followed by 11an minus 4 plus 7. You'll notice that the lead coefficient in each succeeding term is the sum of the two coefficients in the preceding,
Oh.
and the difference between the coefficients, the second term is either plus the third, or 1 plus the first, or the first minus 1. 3, 2, 5, 6, 11, 10, they alternate. So whether you can put that all into a single equation.
Okay, so you said that the lead coefficient is the
My bet is that the next coefficient on the way down
It's gonna be 21.
minus, and it will be plus 22, because it's
and then
plus
it's
1 rather than minus 1.
right. So how are you getting the second coefficient? You're getting it
One
from
more than 21, and then the next term I'll have it at 1 next 22.
Oh, I see.
And then the next one will be 43 minus 42.
I see. Plus 42, yeah. So what Sam's saying is he thinks the pattern is you add the two coefficients to get the next lead coefficient, and then you add the two coefficients and add or subtract 1.
And the other pattern,
Oh,
Yeah, the next term on the right side is actually double the previous term on the left side. So it goes like 3
Oh,
to 6,
yeah.
5 to 10, 11 to
right.
20.
So here to here it doubles. Yeah. If we have some constant here, so if we have something like this, then the next term is going to be ck plus ck minus 1, and minus k minus 1, and 2ck and minus k minus 2. So this is the claim, how the coefficients are building up. And can we solve it from here? So,
but obviously the order is going to be 2 to the end.
right,
That stems from the original, because 2 to the end, local powers minus 1 to the end.
right. Yeah, so now we've seen the pattern in the coefficients. I still don't see exactly how we would solve this equation for the general k, other than we'd get, well, so I want to write this down. No, I don't think I want to write this down. So,
Sarah,
yep.
could you actually just explain in the last line that you've written here, CK plus C?
Oh, yes. So
What each thing is.
right. So what the pattern here is, if we know what our constant is on an minus k and on an minus k minus 1, so if we've done k steps or k substitutions, then the claim is that when we make the next substitution, what we're going to get on a times a sub n minus k minus 1 is the sum of these two constants, and what's going to be on the a n minus k minus 2 is going to be 2 times this first constant. And we could see that simply by substituting in this formula for this. Does that make sense? Is everybody clear on this? Anthony?
I have a question going back a bit. I
Mhm.
don't see why the a sub n on the other board
Mm-hmm.
is in the form r to the n, which is, I thought, what we wanted.
Yeah, that's what we're trying to. Oh. So what we end up getting, rather than just getting something r to the n, we get. So we have all these roots. Can I erase this since it didn't really lead us anywhere? So what we end up getting is we have this characteristic equation. And this has some roots, R1 to RK. And in fact, any Well, in fact, the solution, given our initial conditions, is going to be some linear combination of powers of these. In fact, so our solution is alpha 1 r1 to the k, alpha 1 r1 to the n plus alpha 2 r2 to the n plus alpha k r k to the n. So what we end up getting is actually a linear combination of these roots. No.
So it's like first you have to find the roots, then once you find the roots, you're still not done. You need to find.
Right, you need to find which combination. And you can find which combination by looking at your initial conditions. So you have some initial statements, you know, we know what A0 up to AK minus 1 are. So, you know, if A0 is 5, then we can say, okay, A0 is 5, but it's also supposed to be alpha 1 times R1 to the 0 plus alpha 2 R2 to the 0 plus alpha k R k to the 0. And so we get some equation in the alpha k's, in the alpha i's. And we'll get k of these, one for each of these initial conditions. And so then we have to solve equations, which we, in theory, know how to do. So, are we reasonably happy with this? Should we do another example? Neil?
After you get the roots, how do you have to put the roots back in the equation in a certain order, R1, R2?
Let's do an example.
I just wonder how you decide what root is your R1.
Oh, it's arbitrary. It's completely arbitrary. Yeah. You'll get, I mean, what constants come out. You have to be sure to make the right constant go with the right root at the end. But other than that, it's completely arbitrary which order you choose.
Can you do an example that has 3?
Yeah, let's do an example that has 3. Okay, so I claim that if I take the following recurrence equation, okay, so here we have a recurrence equation, and hopefully I multiplied right, and we want to solve it. So what we do is, well, we say, first, what's the characteristic equation? That's when I substitute in r to the n for these guys. Now I pull them all over to the left-hand side of this equation. So I get r to the n minus 2 r to the n minus 1 minus r to the n minus 2 minus 2r to the n minus 3 is equal to 0. Plus. Okay, so now I divide through both sides by r to the n minus 3. The reason I'm doing this is I want to end up with a constant term out on the end. I want to end up with a polynomial. So I get r cubed minus 2r squared minus r plus 2 equals 0. So this guy's my characteristic equation.
You do that so you get a constant on the end?
Yeah, I do that so I get a constant on the end.
Then you can solve
Otherwise, I just have, you know, a whole bunch of powers of r out at the front. And so I guess I should assume r is not 0 here. Okay, so now what's going on?
Ask you,
Sure.
I'm seeing how you're going from the equation with r to the n minus 3 in the denominator to that.
Okay, so the n minus 3, it divides through each term. and I just subtract n minus 3 from each term. So, x to the k over x to the j is x to the k minus j. So n minus 3 is r cubed, etc. Okay, so I have this equation, and unfortunately I cooked it up over where the video couldn't see me, and so I know what the roots are. This factors as...
How do you solve those if you don't already know the answer?
How do you solve them if you don't already know the answer?
Assuming that there are integer solutions, the product, and Tara wouldn't give us anything other than that, the product of the solutions is going to be the constant term. So factor into 2 and see whether 1 minus 1, 2, or minus 2.
Okay.
Solve.
Right. So what Sam's saying is, if they're integer solutions, which they should be because hopefully Shai was nice on the problem set, then all you have to do is look at this constant term, because the constant term is going to be the product of this, and this.
The proviso is that the lead coefficient is 1.
Oh, yeah. Yeah.
That's the only set of those are the only numbers we're going to get in this class. So you can
Yes.
assume
Yes. I mean, certainly, if our recurrence relations come from algorithms, we're not going to do 0.3 times, the previous step. And so, yeah, all these guys are really going to be integers. And so we should be okay. So what Sam said, Sam's hint for trying to factor this if you come across some horribly messy equation, is that if you have a 1 out here, and, well, then you can look at your constant term here, and your solutions must be factors of this constant term. They must multiply together to give you this constant term. So just look at a factorization of that constant term and figure out which possibilities work. In this case, we have 1, 2, and minus 1, which multiply together. That doesn't look right.
You would need 2 negatives
Oh,
and a
yeah.
positive of a combination of 1 and 2.
Right. That's right.
So is it fair to say that the characteristic equation is exactly equivalent to your original equation?
It's not.
No.
So it's not equivalent. It's just an equation that you've derived from your original recurrence relation.
the only other root of the recurrence equations are equal 0, assuming that r is not equal 0.
Right. So we could also, here I divided by r to the n minus 3. That guy would have given me a solution r equals 0. I'm assuming that doesn't happen. Because I guess when we write down our final solution here, if we have an r equals 0 here, that's not really contributing. That's not contributing anything at all. Except when...
But most likely that would not be consistent with the boundary.
Exactly.
Because that would mean everything.
Because then yeah, that's right. So, okay, so now we have our characteristic equation. Let's have some nicer initial conditions. I'm not letting Sam give us 17 again. So,
6, I have 28. Try 6 and 28. No.
1 and
1, 2, and minus 1. So our solution is supposed to look something like constant times 1 to the n plus second constant times 2 to the n plus a third constant times minus 1 to the n. So now we can find out what our constants are in this particular example because we know what our base cases are. So our base case, well, we say a0, that's 0. But it's also, if we plug 0 in for n here, we get alpha 1 times 1 to the 0, that's 1, plus alpha 2 times 2 to the 0, that's also 1, plus alpha 3 times minus 1 to the 0, that's alpha 1. So we get alpha 1 plus alpha 2 plus alpha 3 equals 0. Our next equation is going to say, okay, let's figure out what A1 is. Well, 1 to the 1 is just 1. 2 to the 1 is 2, so I get 2 alpha 2. And minus 1 to the 1 is minus 1, so I get minus alpha 3. And then lastly, I get 2 is equal to A2, which is alpha 1 plus 4 alpha 2 plus alpha 3. Okay, so now I have to solve this system of linear equations. And yeah, I do Gaussian elimination.
Well,
So
let's simplify this. Subtract the first from the third.
yeah, subtracting the first from the third gives us what A3 is.
Gives us what A2 is.
I mean, in fact, you don't have to use Gaussian elimination. You can use whatever your favorite method for, whatever is. So, let's see, A2 minus A0 is equal to 3 alpha 2, which is equal to 2. So alpha 2 is equal to 2/3. And then,
You can add A0.
right, if we add these two, then we get 1 is equal to 2 alpha 1 plus 3 alpha 2. And so alpha 2 is minus a half. Is that true?
Okay, alpha 1 is minus that.
Yeah. And then finally, we can plug that back into the first one. And so we have 2/3 minus a half plus something is equal to 0. So alpha 3 better be minus a sixth, positive sixth. Right. Yeah. So what does our final answer look like? Well, our solution says that AN must be minus a half times 1 to the n, that's just 1, plus 2/3 times 2 to the n minus 1/6 times minus 1 to the n. And so if we did out, 100 terms of this sequence, we could check that indeed this was the right formula. So I'm a little afraid to do that because I'm a little afraid of my multiplication out of these. So that's 4 plus 1 is 5 minus 0. So A3, I predict is, did I say 5? Yeah. And so now if I plug in 3 here, I'm going to get minus a half plus 2/3 times 8 plus minus a sixth. Well, plus a sixth, that's going to end up being, because there's a minus 1 to the 3. Let's see what this adds up to. This is minus 2/3 plus 8 times,
Minus 1/3.
right, minus 1/3, no, it's,
So it's 16/3 minus 1/3.
Yeah.
15/3.
yay, it's 5, so we actually did the right thing. For the first iteration, for if you do this algorithm on 0 things, then it takes 0 time. If you do this algorithm on 1 thing, then it takes 1 step. If you do it on 2 things, it takes 2 steps. So we have to have some initial conditions. Once we do that, we say, well, here we have this formula for AN. Let's see what happens when we plug in 0 to this formula. When I plug in 0, I put a 0 here, so this is 1 to the 0, plus A2 times 2 to the 0, plus alpha 3 times minus 1 to the 0. Now when I multiply these things out, 1 to the 0, 2 to the 0, and minus 1 to the 0 are all 1. And also, I assume from the beginning that this is equal to 0. So I get the equation 0 equals alpha 1 plus alpha 2 plus alpha 3.
And that's an initial condition.
And that's from one of my initial conditions. From my second initial condition, I say, okay, A1, well, by this formula, it's supposed to be 1 to the 1 times 2 to the 1 plus minus 1 to the 1 times these constants. And also it's supposed to be 1 by my initial condition. So, I get this. I could also, well, I know now that A3 is supposed to be equal to 5 simply by plugging into here. I can now set up another equation that says 5 equals A3 equals, well, alpha 1 times 1 cubed plus 2 cubed times alpha 2 plus minus 1 cubed times alpha 3. And that would give me a fourth equation. Of course, it would be dependent on the other 3. It's not really relevant. But I guess you could choose the equations that looked the prettiest and solve those for your alphas. The book explains how to prove this theorem, and so that's exactly, that'll exactly tell you why it is that you take these combinations of roots. It turns out what we're doing, so when we were studying linear algebra, and I'll talk about this at the end, maybe. When we were studying linear algebra, we wanted to look, we looked a little bit at recurrence relations, and what we did was we got a matrix that sort of described our recurrence relation, and then we got a closed formula by diagonalizing that matrix and then taking it to some big power and multiplying by the initial conditions. And essentially what we're doing here is the same thing, except we're hiding all the linear algebra. So if you think about what it meant to, well, no, we'll talk about it, in 15 minutes. What happens if our characteristic polynomial is r minus 2 squared? So this would come from the recurrence relation an equals 4a n minus 1 minus 4a n minus 2. So I'd get this recurrence, I'd say, okay, now I have r squared equals 4r minus 4, so r squared minus 4r plus 4 equals 0. And so I factor this. I say, okay, this is r minus 2 squared. And now I'm in trouble. My theorem doesn't apply. I don't have 2 distinct roots. What actually happens in this case is something that's going to remind us a little bit of partial fractions. So that's really, like I'm pulling this out of nowhere. But what happens is, in this case, my answer looks something like alpha 1 times 2 to the n plus alpha 2 n times 2 to the n. And if you remember how we did partial fractions when we had, when we wanted to factor this, we ended up with something that looked like this. Squared? Nope, not squared. And so the same thing's going on here. I sort of repeat my factor each time, but every time I repeat it, I add a copy of n. So if I had if you don't remember partial fractions, then, don't worry about this. What? Okay, so the same thing happens, if we had r minus 2 cubed, we'd end up with something like alpha 1 times 2 to the n plus alpha 2 times n times 2 to the n plus alpha 3 times n squared 2 to the n. So the rule is, if you have a repeated root, then what you do is you have some constant times that root to the nth power plus another constant times n times that root to the nth power. If it were cubed, well, then the same thing happens. You have a constant times 2 to some power plus a constant times n times 2 to that power plus a constant times n squared times 2 to that power.
It will be 2 to the power, that power, times the general polynomial to the m minus 1 degree, where m is 2.
Exactly. So if I have r minus 2 to the k, what my solution looks like is alpha 1 plus alpha 2n plus alpha 3n squared plus alpha 4n cubed plus all the way up to alpha k minus 1 n to the k minus 1 times 2 to the n. So I have the general polynomial of degree k minus 1 times 2 to the n. Joe?
How would you do if you had like r minus 2 squared times r minus 1?
Good question. So that's the next thing. You know, this, so generally, if we have r minus 2 squared times r minus 1, we have, well, okay, so this r minus 2 squared gives us an alpha 1 plus alpha 2n times 2 to the n. And this guy gives us an alpha 1 times 1 to the n. Whoops. Alpha 3 times 1 to the n. So what you end up doing is if we have, this is the most general thing we can write down. If we have roots r1 up to rt, and these have multiplicity m1 up to mt, so that's how many times each of these roots occurs. So these are roots, how many times they occur.
You could have 5 roots with M1.
Yeah.
Okay.
So we could have, 2, 2, 2, 3, 4, 6, 6, 8, 9, 9. And so how I would write this here, I would say, okay, I have 2 with multiplicity 3. I have 3 with multiplicity 1, 4 with multiplicity 1, 6 with multiplicity 2, 8 with multiplicity 1. Writing down these arrows isn't really important, but you just have to keep track of the multiplicities and the roots. Okay, so this would be really complicated, but we could still write down the general solution and solve for a general solution using our initial conditions if we, God forbid, needed to. What the general solution in this case is going to be is exactly, take this guy. This is going to give us a general polynomial of degree m1 minus 1 times r1 to the n. So we get that. This r1 occurring m1 times contributes this much. Does everyone see how that's the right thing? What's going on is I said, well, let's say this occurs 5 times. Then I'm going to have a term for the 0th term, an n for the first time it occurs, all the way up to 5 times n to the 4th. And now I just replace my 5 with the general multiplicity. And then I multiply it by this root to the nth power. So is everyone clear on this term so far? Then I just add to it exactly this for each of the next couple terms. And this just looks awful. You would never, well, so we write this down for the next term, et cetera, yada, yada, yada. We write it down for the last term.
Sorry, can you hand out the right subscript on the, it just
Oh.
goes to 4 and 4.
Okay. Yeah. So in my handout, there's probably a typo because, yuck. Okay, so let's do. Let's write this out for this example, just to be, or whatever. Okay, so we have 2 occurring 3 times. So that means that 2 gives us an alpha Sam's right, we should be using constants because these subscripts get really annoying, but
That's simply a second degree polynomial array.
sure.
You can abbreviate all of these.
Sure. So what Sam's saying is we can abbreviate all of these polynomials to be, this has to be a polynomial of degree 4, this has to be a polynomial of the multiplicity -1, etc. So here, let's see, I'm supposed to go up to multiplicity 3, so this was enough.
It could be written capital P's up to parentheses n, all times 2 to the n, plus P1n, 3 to the n, plus P1n,
Right.
4 to the n. It makes it simpler, then you can put it into a summation sign if you understood exactly what.
Right. So what's going on is this is just some polynomial times 2 to the n. And it's a polynomial of degree 3 minus 1. So P sub 3 minus 1 of n. And I guess I should... What I should say is that this polynomial depends on something. This isn't going to be the same polynomial as the polynomial for any of these others. So, yuck, we have to have all these subscripts that mean whatever they mean. But so in any event, you're never going to have to do something this ugly. So let's do something slightly prettier. Let's say we have r minus 2 squared times r minus 1. This is Joe's example. And this is probably the worst we'll see it. So what's going on here is I have to write something like c plus dn times 2 to the n plus, I can't use e now, times n. Alpha, beta, and gamma now are all constants. I got sick of the Roman alphabet, and I moved to the Greek. So, so this is what my solution for, if my characteristic equation is this is what the form of my solution is going to be. Are we clear on this? Is this okay? Okay.
Just have to give us three initial conditions.
Right. And so in this case, we have something of degree 3, so I'd need 3 initial conditions. And then we could solve for alpha, beta, and gamma.
So alpha, beta, and gamma instead of alpha 1, alpha 2, alpha 3 here.
That's right.
Previously when you had the alpha and the two subscripts, did the first one represent which root it is and the second one which multiplicity it is?
So yes, that's exactly right. So these are all corresponding to root 1, and then they go up to the number of the multiplicity. And I guess this should really go up to 4.
Or you could have just started with 1 and then gone up to 5.
Yes. Yeah, absolutely. And probably I did in the notes. Oh, I didn't? Okay, then I didn't. So are we reasonably happy with this? Okay. We haven't done anything like this yet today. And that's too bad. I mean, well, we know something from the Master's theorem about the order of growth of this. But we don't know a closed formula for solving this kind of recurrence relation. So I'm going to quickly go through solving these kinds of recurrence relations, and we'll get to one example. And then hopefully we'll have 5 minutes at the end to talk about linear algebra and the Fibonacci numbers. Okay, so what's going on with these? These recurrence equations look like this. They look like an is c1 times an minus 1 plus c2 times an minus 2 plus all the way down to ck an minus k. And that part's okay. This we know how to solve mostly from the linear homogeneous stuff. And then we add on some function of n. And this is exactly, so equations of this form are called linear, non-homogeneous recurrence relations with constant coefficients, and maybe I'd call this one degree k. So all the words are the same except now this is non-homogeneous. What makes it non-homogeneous? Well, exactly this extra function out at the end. Okay, so great, we want to solve these. The Master's theorem tells us how to find the order of growth depending on how fast f of n grows, but it doesn't tell us anything about how to find a closed form for the recurrence relation. So how we do that? Well, we have to make use of a couple theorems. The first one isn't very useful, but it tells us something interesting. What it says is if we have any, like if we can find one solution, and that's the hard part. I haven't told you, we don't know how to do that yet. So if we can find one solution, we'll call it A sub n with a little p up here. That means it's a particular solution. Then every other solution is going to be of the form an of p plus some other a sub n h, where this guy is a solution to this homogeneous part. So where a and h is a solution to the homogeneous part C1 a n minus 1 plus blah 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 plus ck a n minus k. So this is something like when we were solving equations in linear algebra, we had the solution of an equation is some particular solution, which we find, who knows how right now, plus some other solution which is supposed to be in the null space. So we had somehow a particular solution plus something that depended on these free variables that we had floating around. Right now we're supposed to think of this part as the free variables. And so any solutions to those we can then add on to a particular solution to get an overall solution. If you have seen anything about differential equations, and if you haven't, you can sort of do this right now for the next 2 minutes or 10 seconds. This is very similar to how you would solve a system of differential equations. And if you've seen that, then maybe you'll see the connection. And if you're interested to hear more, then come talk to me after class. It turns out that you solve systems of differential equations using linear algebra in the same way. And so the solution arises as a particular solution plus some solution of the free variables or some solution from the null space. So great. I mean, this theorem tells us that if we have one solution, then we have a whole bunch. But it doesn't tell us how to find one solution. So the question is, how do we find one solution? We can only do it when f of n is the form a polynomial times an exponential. So let's assume f of n equals a polynomial times an exponential. If we have logs in here, we're still kind of screwed. I mean, when we had the Master's theorem, we could sort of deal with things like this. We couldn't deal with things when we had, n log n there, and we still can't, I mean, if you can solve it another way, great, but this theorem doesn't allow us to solve it that way. So if our function looks like this, then the claim is a solution is, well, there are two cases. If this s is a root of our characteristic, or there are two cases. So S could either be a root of the characteristic equation that comes from this homogeneous part, or it could not be. We're sort of happier if it's not. So S is not a root of the characteristic equation. In that case, a particular solution is in that case, a particular solution is this guy. This is a polynomial of the same degree as this polynomial, but with possibly different coefficients. We have to figure out what those are. And this is just the exponential to the n. And if it is a root, then what we do is take the same thing, but we multiply on the front by n to the m, where m is the multiplicity. Okay, so we have these two possibilities. And the reason we're multiplying by n to the m is just to push this solution out past the possible solutions that we would have gotten from the characteristic equation. So this makes the degree of this solution higher than the degree of the solutions coming from the characteristic equation. So it just sort of forces a solution to exist. That's not one that we already would have known about. So let's sort of apply this theorem. I mean, it seems confusing and abstract, and let's do an example. Let's look at the triangle numbers. So I'm in trouble because this isn't a recurrence relation, right? I better make it into a recurrence relation. How is it? Right. So I have n minus 1 plus n. I can define the triangle numbers recursively. And now let's go find a formula for the triangle numbers using this recurrence relation stuff. And I guess my initial conditions were that A0 was 0 and A1 was 1. Okay, so let's see. So I can think of this as n times 1 to the n. Now I have to, and in fact, you have to be careful when there's no exponential here. You have to think of this as a 1 to the n, and be careful exactly when 1 is a root of this polynomial, and I hope it is. So this guy gives us the homogeneous part. That looks like a nice simple homogeneous part. So we get r minus 1 equals 0 as the characteristic equation. Are we clear on this step? Anyone, any questions?
Why did you have to add on a 1 to the n?
So what I did was I said, okay, this is the same as r to the n equals r to the n minus 1.
Right.
And so now I subtract. So I have r minus r to the n minus 1 equals 0. Now I divide through. I take out all the copies of r to the n that are, I take out all the copies of r that I can and divide them out. And I end up with r minus 1 equals 0. So I divide this guy by r to the n minus 1. To give that. Is this step clear? Okay, so now we really do have to be careful about the particular solution because 1 really is the root of my characteristic equation, and I have a 1 here. So I claim that a particular solution is going to look like I have to multiply by n out in the front. because this has multiplicity 1. So I'm supposed to multiply by n to that multiplicity, so that's just n to the 1. Now I get a polynomial of the same degree as this guy. So p0 plus p1 n. And then I multiply it by s to the n. Is everyone clear how we went from
It's not
here to
clear
here?
why we had to be careful that the 1 was one of our roots.
Okay, so in this theorem we had two cases, when s was a root and when s wasn't a root of the characteristic polynomial. In this case, when you have this polynomial sitting out in the front, you have to be careful.
So that's S right there.
Yeah, so this 1 is s. And so now we're in the case when s is a root. And so we're in this second case.
Of multiplicity n,
Yeah, of multiplicity m.
and then in this case n.
And in this case the multiplicity is 1.
Oh.
So we multiply by an n to the m, n to the 1. So great. Now I have something that I think is a particular solution, and I have to solve for those constants, again using my initial conditions. So I know that a0 is supposed to be 0. On this side I get n to the 0 is, oops, no, 0 to, oh,
No.
I don't want to use these initial conditions. I want to use,
You need the initial conditions.
what?
You don't need the initial conditions at the moment.
Oh,
You have to
oh, right,
find constants P0 and P1,
right,
so that equation applies for all n. That's a
Right.
particular-
right. So here I have my particular solution. I've just now multiplied through by the n squared. And I want to ensure that this satisfies my recurrence relation, an equals an minus 1 plus n for all n. So on the one hand, it's p0. So on the one hand, it's p0 n times p1 n squared. On the other, pardon?
Plus, not times. P0 and plus P1 and squared.
Yes.
You would say times.
Oh, sorry. On the other hand, it's supposed to be an minus 1 p plus n. And this, according to the formula, is n minus 1 times p0 plus p1 times n minus 1 squared
Plus n.
plus n. Right.
So how do you get that third line from the second?
This guy?
No, the third line one.
This one?
That one, yeah.
So I said on the one hand, this is supposed to be equal to this by this formula.
Okay.
On the other hand, it's supposed to satisfy the recurrence relation.
Oh.
It's supposed to satisfy an p is equal to an minus 1 p plus n.
But this last equation has to be satisfied for all n. We have to do P0 and P1, so that
Right.
the answer is
What?
independent.
An, of, I don't even know how you say that. An.
Let's just erase it so we don't have to say it.
Just say an.
Yeah, so this, we're just finding a particular solution.
Because finding the root of the
Is P an exponent there? Or is it
It's,
just a
Superscript, and we're erasing it.
So
Yeah.
this is equivalent to that last leap of faith where we did alpha, but now
Yeah.
we're doing a second leap of faith that's tailored to this type, right?
So we're doing so now we're applying this second theorem, which we haven't proved, and so yes, I guess this is a leap of faith that says, here, this is one way to find a solution.
Right. And what do the P naught represent?
These are constants, and we have to figure out, yeah, these are constants. Yeah, there's like 8 million constants today, and if you can keep track of them, then you're a step ahead of me, probably.
So that second line there, the P naught n plus P1 n squared.
That was just multiplying this out.
No, the second line. That is our particular solution.
Yeah. Well, we have to find constants such that this works.
That has to equal the formula.
Yeah. This has to be equal to
For any
this.
And what's the 1 to the n? That's S,
This is S, yeah,
which is that one.
which is Yeah. Which is this 1 to the n. That's right.
So we find our particular solution, which is p sub 0 n plus p
Mm-hmm.
n squared. Then we're trying to find a constant.
Yeah, so now we're trying to find constants so this works.
And I don't quite see how we get from the third to the fourth line.
Here to here?
Yeah.
This is just substituting in this formula now for n minus 1.
Okay.
It's saying, okay, n minus 1, that means it's p0 times n minus 1 plus p1 times n minus 1 squared. Is everyone clear on this algebra? There's a lot of algebra here, and if you get lost in a step, then it's very confusing. So I want to make sure everyone's with me. Okay. So, great. I have this p0n plus p1n squared, and I have this other one. Let's simplify this equation. Squared minus 2n plus 1, and then plus another n. And I'm going to have to go over to the other board now and put these all together. Okay, so let's see. We have a p0n minus p0 plus p1n squared minus 2p1n plus p1 plus n. And now this is supposed to be equal to p0n plus p1n squared. So we have this, and we have this, and they're supposed to be equal.
We can get rid of the p1 n squareds.
Yeah, so
Get rid of the p0 n.
great. So what we can do is subtract this p1n squared over this side, and subtract the p0n, and it cancels out this. And what we're going to be left with is minus p0 minus 2p1n plus p1 plus n is equal to 0.
Now put it in.
So what I've done was I've said, okay, cancel p0n and p0n, and cancel p1n squared and p1n squared.
It feels like you just went in a circle, substituting one thing in, and then you do a line,
Yeah.
and you substitute it back in again, and you end up somewhere different somehow.
But we've added in that.
We added the n. That was the difference. So we applied, so I mean, we're sort of doing this inductive thing or something, right? I mean, we assume the formula works for n minus 1, so therefore plug it in, now set them equal to each other, and then figure out what your formula must have been to begin with. So is everyone okay from here to here?
I'm sorry, I missed the step from.
So I have these two sides are equal, these two sides of the equation. And so I just canceled out this p0n with this p0n. You know, I subtracted from this side to this side, and they went to 0. And I subtracted this one off from this one. And so what I'm left with is this term, this term, this term, and this term. Okay, so what I have now, when I do this all out, let's see, the constants on the ends are going to be 1 minus 2p1 times n, and then plus p1 minus p0. This is supposed to be equal to 0.
That has to be true for all n.
This has to be true for all n, and so what this means is that p1 minus p0 better be equal to 0, and 1 minus 2p1 better be equal to 0 as well.
So p1 equals p0 equals a half.
So what this finally tells me, I can solve this equation to get p1 equals a half. And this equation tells me that p1 is equal to p0, so p0 also equals a half.
Why do those two parts have to be zero?
They both have to be 0 because this has to be true for any n. And so, well, if I think of this side, if I think of this as a polynomial in n on this side, I have 0n plus 0. So the constant term on n better be 0, and the constant term itself better be 0. that okay? There's some skeptical looks. Okay, great. So I get P1 and P0 equal to 1/2. What does that tell us? You know, now I've done all this algebra. We're all confused. Where are we? What have we gotten? Well, what we've gotten is we come back here, and we have this formula now for AN, this particular solution. What it is, now I can plug in my P0 and my P1. Let's erase all of this. So my particular solution is when I plug in 1/2 for each of them, so I get 1/2 n plus 1/2 n squared. What does that mean? Well, I mean, let's rewrite this. This is n squared plus n over 2. That's the same as n times n plus 1 over 2. Thank God we got the right formula. You know, I mean, that's our formula.
We have a particular solution, now we want the general solution.
Right, right. So Sam's right. We're maybe jumping the gun. We have a particular solution. We have to find the general solution. The general solution is supposed to look like, well, we have to go back to our characteristic equation. And the general solution is any solution to the characteristic, any solution to this homogeneous equation plus our particular solution. Okay, so our homogeneous equation is just this, an equals an minus 1. Well, we could solve this using the methods that we talked about at the beginning of class. But on the other hand, if we know that a0 is 0, which it is by assumption, then a solution to this guy is going to be equivalently 0. Right? I mean, if a0 is 0, then a1 is 0, and a2 is 0, and a3 is 0. And so we could figure out what the solution is, but what it's going to turn out to be, just because this is sort of a silly recurrence equation, is just an equals 0.
I was saying that you'd cut a step out.
Right, so I'd cut a step out. So great. Now we have, this is a particular solution. The general solution is going to look something like this solution plus a solution to our homogeneous, our associated homogeneous.
The solution to the homogeneous is k times 1 to the n.
Yes.
And 1 to the n is 1, so it's just k, and the k happens to be 0.
Right. And so what we have to do now, we have a little more work to do. We have to go back to the beginning of lecture and remember how to solve a homogeneous system. This, we just said, well, you know, this was a really easy one. We only had one root, and it only had multiplicity 1. So the solution to it looked something like alpha 1 times 1 to the n. And in particular, if we go to solve this, well, 1 to the n, that's just 1. So an equals alpha 1. And also, we happen to have the equation from our initial solution, from our initial situation that a0 was equal to 0. So 0 equals a0, which is also equal to alpha 1. Therefore, alpha 1 is 0, and so this is the same as alpha 1 equals 0.
So how do you know what to choose for your initial? I mean, if we wanted to say maybe alpha 1 equals 1.
Right. If we
mess up, I mean, a sub 1 is 1 rather than a sub 0 is 0.
if we had started with a sub 1 equals 1,
When we get alpha 1 equals 1, and that would change our...
no. We'd end up with yes, and I'm not sure why I have to think about it. I mean, there's something we're doing wrong there, and I can't see what it is on the fly.
We have to be careful about what we choose.
Yeah, so you have to be careful about your initial solutions, and you'll get those as part of your initial data or whatever. So why?
If you're putting in alpha 1 equals 1,
A1, yeah.
A1
A1.
instead of A naught.
Right, if you're putting in A1 equals 1, you're going to have to subtract that A1 from your specific solution to balance it. Specific solution.
Right.
Yeah, the specific solution
So-
is solved with.
The specific
Yeah,
solution
so-
is basically stating this is what happens at the tail. And you have to start at a particular point. If the particular point was 0, there's no problem. If the particular point is 1, there's very little problem. You only have to subtract one of the terms.
Right. So what Sam's saying is actually we're okay. The particular solution is computing what's going on really far out. And so you just have to be careful about where you're starting. And, you know, this sort of takes care of that. And so if we were starting at 1, we'd have to subtract 1 off from this initial solution. And then add it back on because it was the solution to that particular solution. So,
So is that something we have to be careful with anytime A naught is not 0? Like in the previous case where A naught was 17? If
I'm giving you 17, let you decide.
probably, yes. But I want to say that always you're going to have A0 equals 0. Is that true? Maybe not.